After watching this video, you should have a fundamental understanding of how you can build an explanation of the equilibrium state of a reaction based on the rates of the forward and reverse reactions in that process, as well as providing an explanation of why the equilibrium point changes in a reaction when the temperature changes. Okay, I want to do a little thought experiment to build a kinetic description of equilibrium and how we can use that description to explain why the extent or the equilibrium point of a reaction can change with temperature. Let's consider this reaction, the dimerization of NO2 to form N2O4, and let's imagine for a moment that we start with a pure sample of NO2. And then we observe this reaction begin, and we monitor the concentrations of NO2 and the formation of N2O4. So at the very beginning of this reaction, we would see a large change in the concentration of NO2. And in fact, if I were to plot the concentration of NO2 versus time, I would see it change a lot at the beginning of the reaction, but that change would decrease as the reaction proceeds over time. In other words, how you can think of this is that as the reaction proceeds, the concentration of the NO2 goes down, so therefore the rate of the forward process or forward reaction would also decrease with time. And that's because as the concentration of the NO2 decreases, the probability of two NO2 molecules colliding with the proper orientation and energy to initiate the formation of a transition state and a product goes down. If the probability of a reaction occurring goes down, the rate of that process goes down. So the rate of the reaction decreases over time as the concentration of the NO2 decreases. Now let's think about the product side. As the reaction proceeds, we start to build up N2O4. And as the N2O4 concentration increases, the probability of the reverse reaction begins to increase. Therefore, we could say that as the N2O4 concentration increases over time, the rate of the reverse reaction begins to increase over time. In fact, if we were to plot the concentration of the N2O4 versus time, it would probably look something like this, where there would be a large change at the beginning, but that change in that concentration would slow as the reaction progresses. So the rate of the reverse process increases over time as the reaction proceeds, and the rate of the forward process decreases in time as the reaction proceeds, again given we start with all NO2. At some point, the rate of the forward process will decrease to a point, and the rate of the reverse process will increase to a point where they are equal to each other. The point at which the rate of the forward reaction is equal to the rate of the reverse reaction, we say that the reaction has reached a state referred to as equilibrium. Equilibrium is when the forward reaction rate is equal to the reverse reaction rate. Now, this is important. It means that the rates forward and reverse are equal, but it does not mean that the concentrations of the reactants and products are equal. This is a common misconception. It turns out that for almost all reactions, when the state of equilibrium is reached, the concentrations of the reactants and products are not equal to each other. And in fact, for example, the concentration of the reactant could be 100 times that of the product. But for now, we can think of the point of equilibrium as being when the rate forward of the reaction equals the rate backwards. At that point, the concentrations cease to change over time, and the reaction has reached equilibrium. Now I want to show you a molecular dynamics simulation to further illustrate this. So in this case, I'm going to do the thought experiment with this dynamic simulation. In what you're looking at here is all the blue spheres represent NO2 molecules, and I have an on switch here, and I'm going to turn it on and initiate this reaction. And as you see red spheres appear, those represent N2O4 molecules. And we can monitor the concentrations here on this graph, which will begin to populate as soon as I turn the reaction on. So I'm going to initiate this reaction, and you can see now that the concentration of the NO2 changes rapidly at first, and then the change of it slows, and at some point the concentrations of the reactants and products stop changing. Notice here that that does not mean that we have equal amounts of reactants and products, but it means that the rate of the forward reaction to produce N2O4 is equal to the rate of the reverse reaction to produce NO2. Now this simulation doesn't really show that the reaction is still occurring in the forward and reverse direction, but you have to imagine that NO2s are reacting to form N2O4s, but that's happening at the same rate as N2O4s producing NO2s. So because of that, the concentrations remain constant over time. This system is in a state of equilibrium. Now, let's go ahead and change the temperature and see what happens. I'm going to increase the temperature of this process. And you can see that as I increase the temperature, there is a change in the concentrations. Notice that, again, the point of equilibrium is established when the concentrations are not changing. That means the rate forward is equal to the rate backwards. But at this new equilibrium point, there are different amounts of the reactants and products. So the question is, how can we explain this using a kinetic argument? To explain this, I've constructed two diagrams, and I'm going to focus first on the diagram on the left, which is often referred to as an energy profile diagram. And the energy profile diagram sometimes is called a reaction coordinate diagram. That's because the x-axis is labeled as reaction coordinate. The y-axis can be thought of as potential energy. And in this energy profile diagram, we can see that the potential energy of the reactant mixture is higher than that of the products. And that implies that this energy difference here, the potential energy difference between the reactants and products, is the amount of energy, in this case, released upon forming products. That can be thought of as the enthalpy of the reaction, and in this case, that enthalpy is negative, or this reaction is exothermic because the reactant mixture is of higher potential energy than the product mixture. And this should make sense too, because we can think that when NO2 molecules collide with the right orientation and energy to form N2O4, we're essentially forming a bond. We know that bond formation is always energy releasing, and therefore we would expect this process to be exothermic. Therefore, in the opposite direction, we can think of N2O4 molecules splitting apart or bond breaking occurring, and therefore we know bond breaking always requires an input of energy, and we would expect that process to be endothermic, and of course it is. If the forward process is exothermic, the reverse process is endothermic. Okay, also on this reaction coordinate diagram, we can see that the activation energy forward, represented by this portion of the graph right here, or this distance in energy space, is smaller than the activation energy in reverse, which would be from this point here all the way up to here. And in general, for exothermic reactions, the activation energy forward is always going to be lower than the activation energy reverse, and the opposite for endothermic reactions. Now, I'm going to come back to this in a moment. I just wanted to point out some features here. And I want to focus now on this diagram on the right. On this diagram, I am plotting the kinetic energy of molecules in this reaction versus the number. Okay? So you can see here that at this temperature, we have an average kinetic energy somewhere around here, and that we know that as the temperature increases, that average kinetic energy shifts to a higher value, and we get a broader distribution. In other words, if I increase the temperature, this distribution would shift to look something more like maybe that. Okay, now let's go ahead and locate the activation energies on this diagram. This is what I mean. Let's say, for example, that two molecules that collide have to have a kinetic energy of this value right here for the reaction to have a chance of forming the transition state and forming product. So any molecules with this kinetic energy or higher that collide, let's say, represented by the area under the graph from that point on, would have sufficient energy to form the transition state and product. Now let's think about the reverse reaction. The activation energy is much higher there, so energy is increasing as we move to the right. That means that the kinetic energy required for the reverse reaction would maybe be somewhere down here. And so the area under the graph from that point on, representing the number of molecules with the sufficient energy to form the transition state, is lower. Now let's look at what happens when the temperature increases. When the temperature increases, both the forward reaction rate and the reverse reaction rate increase. All the rates of the reactions go up, forward and reverse. But we can see something interesting happens. If I take a look at the forward reaction, I can see that now I go from this area, representing the number of molecules that have sufficient energy upon collision to form transition state, goes from that to this. So it goes up a fair amount. But if I take a look at the reverse, it goes from this little amount to this, which is a much larger increase percentage-wise in the number of molecules that have sufficient energy to react reverse. What that means is that the rate of the reverse reaction goes up more than the rate of the forward reaction. Well, let's think about that. If we increase the rate of both reactions, but the rate of one direction goes up more, that means we would start to shift the reaction towards, in this case, the formation of more reactant, or more NO2, until, once again, the rates equilibrate as this concentration goes up a little bit. Once the rate of the forward process, again, is equal to the rate of the reverse process, the system is at equilibrium. But now at this new temperature, the equilibrium concentration of the NO2 is higher, and that's because the rate in the reverse direction went up more when the temperature went up than the rate in the forward direction did. Now, I can kind of summarize this by saying the following. The higher the activation energy is in a reaction, reverse or forwards, the more sensitive that direction is to temperature changes. In other words, if I increase the temperature, the direction of higher activation energy will experience a larger increase in rate. That will result in a shift of the extent towards the other direction. In other words, for an exothermic process, increasing the temperature causes the rate reverse to go up more than the rate forward. Therefore, we see a shift and formation of more of the reactants as the temperature change occurs, causing the equilibrium concentration, once the rates are equal to each other, of the reactant to be higher. Now let's think about the opposite. If we cool the reaction or lower the temperature, the side with the higher activation energy again is more sensitive to that change in temperature. That means that a reduction in temperature will lower the rate of the reverse reaction more than it will lower the rate of the forward reaction. Therefore, we would see a shift to forming more N2O4s until the rates once again equilibrate. So, in general, we can say the direction of higher activation energy is going to experience a more dramatic change in rate, be it an increase from increasing the temperature or a decrease from decreasing the temperature, and therefore that is why we have a shift of the extent towards, for example, the reactant side as temperature increases in an exothermic reaction, or the product side as temperature decreases in an exothermic reaction. Okay, that's a lot to think about. So what you might want to do now is construct a diagram for an endothermic process and see if you can build the same argument based on the rates forward and the rates reverse.